which is about a lot more PV goes in our T things. And we should finish this probably Monday, because we don't really have a lot with this particular chapter. And then chapter 6 is thermodynamics. But then 7 through 10 isn't as much math. So that's nice. Something to look forward to. We'll be looking at electron configurations and atomic numbers and Lewis structures and things like that. So we'll finally kind of get a little bit away. But thermodynamics is going to be more math, which we'll probably get into next week. So again, let's go through chapter 5, some more of our classes. And I'll be honest, I don't really know what I'm teaching you today because I was up to 1:30 grading. So we'll see what's on these slides. I know I went over them Monday, but I don't remember. So we're going to start with mole fraction. If we know that our moles and our pressure are related, we can get a mole fraction. So the fraction of the total pressure of a single gas contributing to a mixture, and we're still talking about a mixture here, is equal to the fractional number of the moles that a single gas contributes. So what does that mean? That means that, let's say, bless you, if I have a mixture, but I have more moles of helium than I have moles of my other stuff, then the moles of helium are going to contribute to pressure that ratio. Now remember, this is a mole fraction, not a mass fraction, because each gas has a different molar mass. So again, we must convert this to moles. We must look at this with moles. So what that means is that PA over P total is going to be related to NA over N total. The fraction of moles of the total sample, we can figure, so if we know our total pressure, and we know how many moles of gas A we have and our total moles, we can figure out PA. Without knowing things like temperature, we're assuming we're at the same temperature, without knowing things like some of our other things we need to know. So that's nice, it just gives us another way to figure things out. The ratio of moles of a single component of the total number of moles in the mixture is what we call our mole fraction. That's just our ratio, and it's shown with this little X that's kind of italicized, of A is equal to NA over N total. Now this isn't a percent, this is our fraction. So this is literally the fraction of NA over N total. This is really our definition of fraction. This isn't really an equation to memorize. If you know what a fraction is, that's a fraction. It's just the part of the whole. And in this case, it's the moles, part moles over the part whole. So this isn't really a new thing. For gas, we can look at volume over 100%. So that just makes sense. So if our XA is NA over N total, if we replace this term here with XA, then we find that our pressure of A is equal to our mole fraction times P total. All that means is I took this PA over P total. This whole thing equals this. So PA over P total is equal to this XA. All I did was replace that NA over N total with XA, and then we solve for PA by multiplying both sides by P total, so we get this equation. Again, not really an equation you need to memorize, but it's just showing how we can relate our mole fraction and our total pressure to get our partial pressure. And it's just based on the fact that if NA over N total is our mole fraction, then that can give us a relationship between our partial pressure and our total pressure. Because again, remember, our volume is the same, our temperature is the same for all of the atoms in the gas. So let's look at an example of that. We want to find the mole fractions and partial pressures. So that's just the pressure of each gas in a tank with a 24.2 grams of helium and 4.32 grams of oxygen at 298 K. That doesn't really matter. What does matter is that what we're given is our amount of our gas in grams, and we can't relate grams, so we will have to convert that to moles. And again, what we're doing is relating grams here. So what we want to find is our mole fraction of Xe, That's just our moles of of our HE divided by our total moles. Our mole fraction of O2, that's just our moles of O2 divided by our total moles. And then our partial pressures. And we can do all that. And there's multiple ways, again, we can figure out a lot of these. For example, we can figure out our partial pressures because we have our moles, we have our temperature, and we have our volume. So there's multiple ways we can do this. And I'm going to go through only one way, but there are multiple ways that will still give you the correct answer. So the first thing we'll do is just find our moles of our two gases. We're given our mass, but we want our moles. So that's our first step. So according to the periodic table, our molar mass of helium is 4 grams per mole. And our molar mass of O2 is 32, 16 times 2 grams per mole. So we can find our moles of each, and then we can find our total moles in that way. So we can find our mole fractions. So that's pretty straightforward, and that's what we're going to do first. So our mole fraction of HE, we're going to find our moles of HE. We were told that we have 24.2 grams of HE. And using our molar mass, 4 grams of HE, grams go on the bottom so they cancel out, equals to 1 mole. So now we know our moles of HE. Then we can find our moles of O2. And again, we're told our mass. And our molar mass is 32. Still having trouble converting from molar mass to moles? Please come talk to me because we're going to pretty much always do this. And you're going to be doing it when you take lab as well, and in 106. So it's really a skill that you're going to be using a lot. So now we know our moles of each of our gases in the mixture. And of course, we have to assume that these are our only gases in the mixture. Otherwise, we'd have to be told differently. So we can get our in total. In total is going to be our moles of HE plus our moles of O2. Now remember, we cannot add together our grams and then convert to moles, because HE has a different molar mass than O2 does. So we must convert to moles first. So that comes out to a total amount of moles of 6.185. So now that we have our total moles, we can figure out our mole fractions. I need more room. So we just figured out our total moles. Now we can figure out our mole fraction. Our mole fraction of HE we'll start with, and that's going to be our amount of moles of HE, which we just calculated, 6.05, divided by our total moles. And you would expect this to be the higher percent of the gas because we have more of it. We have a lot more moles of HE. So that's going to contribute more to the pressure, because remember, the more moles, the higher your pressure. So you should already be able to conceptually be able to think about this. Notice our total moles, HE is contributing the most. We have 6.05 moles of HE. We only have 0.135 moles of O2. Again, remember, we cannot compare the grams. In this case, we have more grams of HE, but that will always be the case. If our gas has a really high molar mass, it might look like we have a lot more of it in grams, but when we actually look at moles, it might be less. So don't just look at grams and make the assumption, well, we have more grams of HE, so we have more HE molecules. That may not be true. It's true here because HE only weighs 4 grams per mole. So always watch for that. Always convert to moles. So 97.8% of our solution, or our mixture, is HE, because if my mole fraction is 0.9787. Oh, sorry, 817. I left off a one. So most of our mixture, if our fraction is out of 1, most of our mixture is helium. And our partial pressure related to helium is going to be a lot higher because we have a lot more of it. Now we only have 1.35 moles, and of course moles cancel out because this is a fraction, so it has no units. Our total moles does not change. So clearly we have a lot smaller of a percent of O2 in this particular mixture. Only 2% of this mixture is O2. So now we know our mole fractions, but we can also calculate our partial pressure of those. And there's a couple of ways we can do this. We can do 3 separate PV equals nRT equations, or we can find our total pressure, and then we can use this, our mole fraction and our total pressure, to figure out our partial pressures. Or you can just do 3 separate PV equals nRT equations, and you'll get the answers. So it's not wrong to do that. It's just a little bit faster to do it this way. So we can calculate our total pressure because we know our N total, and of course we know volume and we know temperature. So if we calculate PA, then we can use this formula. We calculate P total, we can use this formula because we know our N total. So finding from N total to find our P total, remember PV equals nRT, and here we're looking at our total. So P total and N total. So to find our P total, it's just going to be our N total, which is at 6.185. Moles. Remember, this must be in moles. Times R times temperature in Kelvin, which it is in Kelvin, so we don't have to do any conversions, and all divided by volume, which is already in liters. And that'll give us our total pressure. In ATM. So now we have our P total. Now we can figure out our partial pressures of our 2 molecules. And again, you should already be able to figure out that the partial pressure being contributed to helium is going to be more than that being contributed to O2 because we have more helium molecules. So just that, you should already have that idea when you're figuring out your answer, especially since you have multiple choice answers on your test and quizzes. So if you're circling something and it doesn't make sense, then you should recheck your work. Because again, you should be able to think about these things. The more moles, the higher the pressure. We have a lot more moles of helium. Again, do not compare them in grams. So our last step is finding our partial pressures, and I ran out of room. Why isn't it letting me copy? That's weird. Whatever. Just do that. Okay, so finishing this, we're looking for, we want to know PHE, and we know PO2. So we know our XHE, and we now know our P total, and we know our mole fraction of O2, and we now know our P total. So now we can figure out those partial pressures. And remember, there's no units on this mole fraction because it's a fraction. So multiply that by our total pressure that we just calculated. And we get our partial pressure of helium to be 11.8. Of course, we're still in atomic mass units. Nothing has changed with our units. And then if we look at PO2, instead we are multiplying that 0.021827 times our total. And of course, the pressure is the same for our total pressure of both. So as you're going through these problems, try not to memorize the steps in working them, but think about what we're actually doing. And apply it, just visualize what kind of systems we're talking about. We're talking about gases. So it makes sense, if we look at these numbers, that because we have a lot less moles of O2, that we have a lot less contributions to the pressure. If we add up these two numbers, we should get our total pressure. Because remember, this plus this will equal to our total pressure. So you can always check your work. It should equal. So again, I really urge you as you're going through these to really think about what you're doing. Don't just memorize steps. So let's talk about, we've talked about just examples. Let's actually talk about how in the lab we look at calculating reactions involving gases. Gases are often collected because, you know, a gas forms, you can't see it. You might see smoke, but you mostly can't see gas. You can't really capture it so much. It's not like forming a solid and we can precipitate it and filter it. So how do we figure out how much gas is being formed? How do we collect gases? So oftentimes what we'll do is in the reaction, a reaction will occur, and what we'll do is collect it over water. Now we don't want a fully closed system because that increases our pressure. The more gas molecules that form, the pressure changes. So to avoid that, we can use something like this, collecting gas over water. And we'll see our water level change. And when you do take lab, you'll do a couple of reactions like this. But there is a problem. And the problem with this is that water evaporates. And when water evaporates, what is it? It's a gas. So what you do essentially when you collect your gas over water is you're going to end up with some sort of mixture where you have whatever your gas that formed. In this case, it's showing hydrogen. This reaction formed hydrogen gas. But whatever your reaction, whatever gas it formed, you also have some oxygen vapors and water, hydrogen plus water vapor molecules, H2O. So you're going to have to use what we've been talking about mixtures, to figure out what is actually being attributed to your gas being formed and not from the water evaporating. So that's going to be important. So the partial pressure of water vapor, we call that vapor pressure. That makes sense. And it depends on the temperature, but you can use a table to figure out what your vapor pressure is going to be whenever you're collecting your gas. And you don't need to memorize this. I will give this to you if it's relevant to a question. Either I'll tell you the vapor pressure, or I'll give you a table. So you don't have to memorize this. And it's silly to memorize that because you could just look it up. If you collect a gas sample with a total pressure of 752.8 millimeters mercury at 25 degrees Celsius, and you know the partial pressure of water, you can figure out how much gas you actually collected. And you can figure out a lot from that. So really, that's what you're trying to do, figure out how much gas is being collected. So this is a kind of table that you might use, and often these tables are given in millimeters mercury. But remember, to use our gas laws, because of R has ATM in that unit, we will have to calculate this to ATM. But most of the time, these are given to you in millimeters mercury. So how'd you use this? Talking about a gas collection reaction at 35 degrees Celsius, this is the partial pressure you'd use for water. If you were talking about the reaction at 100 degrees Celsius, this is the partial pressure you'd use for water. So that's just how you use the table. Again, you don't need to memorize this table. That's not necessary. We don't need to have that kind of thing memorized. It can be looked up. It'll be given to you. But let's look at an example. Why didn't you start? Oh, it did start. Oh, sorry. Gonna restart it. I don't know why it does that. Trying to give you more time. Okay. I'm not gonna touch it again. So let's look at an example. Now the key to remember these, we didn't really just learn anything new because we've done partial pressures. So we're just applying what we've talked about. So let's say we collected 1.02 liters of O2 over water at 293 Kelvin, so we know our temperature, with a total pressure of 755.2 millimeters mercury. And we want to know how much O2 we have. We want the mass, but our first step is going to find the molecules, of course, because PV equals nRT, that's our moles. So we have our partial pressure. The first thing, as soon as you see collected over water, you want to look up your vapor pressure. We're at 293 degrees Kelvin. Well, this is given to us in degrees Celsius. But that's okay. All we have to do is subtract 273. So this is really 20 degrees Celsius. Now we don't want degrees Celsius for our calculation. We're literally just using it to figure out what's the correct partial pressure of water. Because remember, in PV equals nRT, we have to use Kelvin. So we have that our partial pressure of water is 17.55 millimeters mercury. So now that we know that, we can calculate this, and this is just the same as all of our other partial pressure reactions that we've talked about. So we know our volume, we know our pressure, we know our temperature, and we now know our partial pressure of water. I don't know why that just did that. So what we can do is figure out our pressure of O2. We know our pressure of H2O, we know our total pressure, we can figure out our pressure of O2. Once we have our pressure of O2, we can use P V equals nRT, because we have our partial pressure of oxygen, to figure out our moles of oxygen. Once we have our moles, we can just use our molar mass to calculate our grams. So the only layer that we're really adding to this is the partial pressure part, and it's really not new. So we just determined that the partial pressure that we need of H2O is at 20 degrees Celsius, and that's going to be 755.2 milligrams mercury. Oh wait, that's our total pressure, sorry. So we figured that out to be 17.55. And of course, our partial pressure of water is always going to be lower. You can calculate this to ATM first if you want, or you can figure out your partial pressure of O2 in millimeters mercury and then convert it to ATM. You're going to get the same answer. I just like to do as little conversions as I have to. This means I only have to do one instead of two. But it both works. So our partial pressure of O2 is just going to be 755.2, our total pressure, minus our vapor pressure of water. Then we have our partial pressure of our O2 gas, which is 737.65 millimeters mercury. And if that number comes out more than your total pressure, you did something wrong, because this is just a partial pressure. Now I do need this in atomic mass units, so I can use PV equals nRT. So our ATM goes at the top and our 760 millimeters mercury at the bottom. So that tells us that our partial pressure in ATM for O2 is 0.9706. So now that we have our partial pressure, we can figure out our moles. Divides both sides by RT, and we see our moles of O2 is going to be equal to our pressure of O2 times volume over RT. So our pressure is in ATMs. We just did that conversion. Times our volume. It's in liters, so we're good. Divided by R. Times our temperature in Kelvin. Don't use that 20 degrees Celsius. So that's going to give us our moles of O2. But this question wants mass, so we're going to convert that. Remember, O2 is diatomic, so its molar mass is 32, which is 16 times 2. So this was just applying what we've already learned to an actual chemical reaction, which is what would typically be done in the lab. So for this one, the answer would be B. What we're looking at here is, again, how many moles. You're only looking for moles of acetylene. So you don't need to know the molar mass of acetylene. It's not necessary, because it doesn't matter. If you needed the mass, you'd need the molar mass. Present in a 500 milliliter sample, that's our volume, of gas collected over water at 20 degrees Celsius and a total pressure of 758 torr. And then, of course, in this case, it gave you your vapor pressure. So you would just go about this the same way we just did. I'm not going to go through this one, but you should, and make sure, following the example we did previously, that you do come to B as your answer. It's the same exact work. Though, do note that your volume is in milliliters and your temperature is in Celsius, so those have to be converted. The only difference from this and the problem before is we stop at moles. We don't convert it to molar mass. which you really couldn't because you don't know the molar mass of acetylene because you don't know what acetylene is, and I don't expect you to. Let's take one more step with gases. Again, this isn't really learning anything new. It's just applying what we have learned about gases and relating it to reactions. So we're using what we learned about reactions and what we learned about gases. So the principles of stoichiometry can be combined with our gas laws to calculate things like theoretical yield, percent yield, how much gas would form, and all of that. We have moles, we know moles, we can do these calculations. So this is just adding to what we already know. This is nothing new. So in reactions of gases, the amount of gas is often given as a volume instead of moles, but we can use our pressure and temperature to calculate that to moles. We've already done that, that's nothing new. The ideal gas law allows us to convert the volume of a gas to moles, and then we can use coefficients in the equation to figure out percent yield, to do all the same things that we do with any other reaction that we've talked about, including combustion, including our precipitation reactions that are aqueous dissolved. So we are still applying the same thing. If it's at STP, which is standard temperature pressure, temperature is 273, pressure is 1, then we can use 1 mole is equal to 22.4 liters. If it's not at STP, we can still calculate the volume, the moles, using PV equals nRT. No difference there. But remember, it must be at standard temperature pressure to use this. If pressure is at 1 and temperature is at 301 degrees Kelvin, can you use this? No, because temperature is not standard. They both have to be at the standard conditions to use this. But if they're not, you can still do it. You just have to do just a little bit more stuff in your calculator. But it's not a lot harder. So if we can figure out our moles of a gas, if we have pressure, volume, temperature, if we know it's at STP, then we can calculate our moles. Then we can use our chemical equation just like we did for all the other examples. And then we can convert that back to volume. So nothing different. Again, we're just adding on a little bit to what we've already done. So let's look at an example of that. We have a chemical reaction. Here's a combustion. Also note, this is not gas evolving because CO is a gas, H2 is a gas, and forms a gas, but it was always a gas. This isn't evolving a gas. Gas didn't evolve from something that wasn't a gas. Just this is a combustion. Now this is a type of oxidation reduction, but it's more specifically called a combustion reaction. So what volume of H2 is needed to make 35.7 grams of CH3O at 700, well actually this is just a oxidation reduction, I'm sorry. It's not a combustion. I don't know what I was thinking. I was thinking that I was grading till 1:30 in the morning, and I'm sorry about that. 738 millimeters mercury and 355 Kelvin. So what we're looking at here is a chemical reaction. We really don't need to know anything more. We want to make sure it's balanced. It is, so we're good. We know, if we know the moles of CH3OH, we can calculate how much H2 is needed. Because according to this chemical equation, we need 2 moles of H2 to make 1 mole of CH3OH. That's what our chemical equation tells us. So if we can figure out the moles of CH3OH, then we can use our chemical equation. But our key is we have to be able to get 2 moles because our relationship of our chemical equation is always a mole relationship, not a mass relationship, not a volume relationship. It's always a mole relationship. So that's our first step. We have to figure out how many moles of CH3OH that we're starting with. So we know we want to make 35.7 grams of CH3OH. And we can figure out how many moles that is. That's fairly straightforward. So that's going to be our first step. Is to take our grams and convert that to moles. Now this one isn't given to us in volume, so we don't have to worry about converting this to grams. We're just going to use our molar mass to convert it straight to moles. We have our mass, so that's all we need to do. Once we have our moles of our, I'm just going to call this methanol because that's what it is, and I don't want to call CH3OH. That's methanol. That's what it looks like. It's a one carbon and an OH. So that's what I'm going to call it because it takes too long to say it. So 1 mole of methanol, and then once we know how much methanol moles that we are trying to form, we can then calculate how much moles of hydrogen gas we needed to start with, because we know our relationship on our equation. So we just use our molar mass to convert our grams methanol to moles methanol, and then we can use our relationship of our equation that tells us that it takes 2 moles of hydrogen gas to form 1 mole of methanol. Now, this tells us our moles of H2. We want to know our volume of H2. That's where our PV equals nRT can come in. Now, we have 738 millimeters mercury and 355 K. We cannot use 1 mole equals 22.4 liters because we are not standard temperature pressure conditions. Pressure is not 1. I know this is in millimeters mercury, but 760 is our conversion, and that's not 760. So pressure is in 1 atm, and temperature is not 273 degrees Kelvin. So we're actually going to have to use PV equals nRT. But hey, we have V, we have N, we will have N, we're going to calculate N. We have our pressure, we can do that. So our first step is to figure out our moles of our methanol. So we are starting with 35.7 grams of methanol. And we can use our molar mass, which you would be able to calculate if you're given the equation. Bless you. Now we have our moles methanol. We can use our periodic table, our reaction that tells us that it takes 2 moles of H2 to form 1 mole of our methanol. So moles methanol can cancel out. We put it at the bottom. And our 2 moles of H2. We could also, and that we're not being asked to, but using everything we're given, we could also calculate what volume of carbon monoxide we need. That's just a 1-to-1 ratio. We're not doing that, but we could. We have everything we need to do that. So when we do this calculation, we get 1.114 moles of methanol. And now we can figure out, oh, sorry. I broke that up in my work. 2.228. I have it in steps in here. Yep.
How do you get moles of methanol?
Sorry. They do. I have it broken up in 2 separate steps in my work. I did the 2 mole and 1 mole separately just for explaining purposes. So 2.228 moles of H2. So now we have our moles of H2. That's what we're left with. Now we can take this, and using our PV equals nRT, we can calculate the volume. Which is basically what we've been doing this whole chapter. Our temperature is in Kelvin. However, our pressure is not in atm. So we do have to do that conversion. And remember, you don't have to memorize this. 760 millimeters mercury and 1 mole. And that'll give us ATM, and that is 0.97105. So that'll give us our liters of our hydrogen gas that we need. And again, you could figure out your liters of carbon monoxide that you need as well. Doing the same thing, it will be different because we won't have this conversion. It's a 1-to-1 ratio instead of a 1-to-2 ratio. So any equation, whatever I'm asking, you're just taking it one step further and applying what we've done with chemical equations to our gas laws. But remember, we can use that conversion. 1 mole is equal to 22.4 liters only if we're at standard temperature pressure conditions. So if we're not, like in this case, you have to calculate using the gas law. So now we're going to spend a little bit of time just talking in general about properties of gases. So remember, our gases expand to completely fill their container. They take the shape of their container. They're really low in density. Clearly, you pick up a balloon. Is it heavy? Now, some gases are more dense than others, and we'll talk a little bit about that, but they're pretty low in density compared to a solid. And the reason why is the molecules of the gases are not interacting with each other. They're not tightly packed. And you can even see that if you take something like foam. Foam is basically polymer that has air in the middle of the polymer. That decreases its density. It becomes lighter. So those gases are contributing to that. They're compressible to an extent. There is a point where you can't compress anymore or your system's going to fail, but that's a thing where your whatever container, whatever it's in, can fail. Of course, you know, if you fill your tire up too much, it might blow up. But you can have it compressible. Mixtures of gases are always homogeneous. So air, we can't tell the difference between it. It's homogeneous. If I take a sample of air here, and a sample of air back there, it's pretty much going to be the same air. And it's fluid, meaning it can float. That's what we mean by fluid. So we're going to talk a bit about kinetic energy, how temperature affects that, things like that, for the last 10 minutes of class. Oh, we're going to look at some Boson distributions. These are fun. We're going to take a little math break. Oh, we'll do more math, just no more this class. I don't think so. I don't think we'll do any more math this class. So let's talk a bit about kinetic energy, molecular motion. So particles of a gas, either atoms or molecules, because of course we could have helium gas, that's not a diatomic molecule, are constantly moving. They're always moving. They're hitting the sides of the containers. We've talked about this a little bit with Boyle's law. The attraction between particles is negligible. When we look at water in the solid state, ice, we have a lot of attraction between water molecules. When we look at water in the liquid state, we have more flow. We still have attraction between water molecules, but not as tightly. Once water gets to the gas phase, the water molecules are no longer interacting with each other. They might bump into each other, but they're not attracted to each other. They behave basically as one molecule. So the attraction between particles is negligible. When the moving particles hit one another, or the container, they don't stick, they just bounce off, they continue moving. You can kind of think a little bit about playing pool and hitting a pool ball with another pool ball. And that'll cause the trajectory of one of the molecules to change, or it could, depending on if it hits another molecule. So there's a lot of empty space between gas particles. One of the reasons why the pressure becomes higher as we close the volume up is because we are forcing the gas molecules to get closer to each other, increasing the probability of them hitting each other, making that space between molecules smaller. So that's what we're really doing because they're not interacting with each other. So compared to the size of the particles, we have a lot of empty space. The average kinetic energy of a gas particle is directly proportional to the temperature. Because as you raise the temperature, the molecules move more. And again, thinking about Charles' law, if we keep pressure constant, as we raise the temperature, the gas molecules move more, and that causes the volume to increase. It takes up more space. If it doesn't take up more space, then the pressure will increase. Because then we're going to get more motion and more hitting each other in the sides. So as you raise the temperature, the average speed of the particles increase. But don't be fooled into thinking all the gases are moving at the same speed, because that's not true. So we're going to look at that. So pressure is equal to force over our area. Well, maybe we'll do a little bit of math. Disappointing. Because the gas particles are constantly moving, they strike the sides of the container, they strike themselves, that causes your pressure. And the result is that the gas molecules are exerting force. That's why you have force divided by area. The average kinetic energy of a gas molecule depends on the average mass and velocity. Now again, this is average because if you have, let's say, a pure sample of gas, even though on average they're all moving the same speed, if it's a pure sample, one molecule might hit another molecule, which might change its trajectory and slow it down slightly. So we do look at average kinetic energy. So Ke is equal to 1/2 of our average mass over our velocity squared. Gases in the same container have the same temperature, so therefore they have the same average kinetic energy. If they have this different masses, the only way for them to have the same kinetic energy is to have different average velocities. Because things that weigh different amounts don't move the same. That just makes sense. So if we have different masses and the same average kinetic energy, that means that the velocities or the amount, how fast the gases are moving are different based on the size. Lighter particles have a faster average velocity than more passive particles, heavier particles. So if we look at these, here are 4 common gases. All have the same average kinetic energy. They don't have all the same velocity. They do have a different velocity. But they all have the same average kinetic energy at or at the same temperature. Of course, if we increase the temperature, that does change. So let's look at velocities. All the gas molecules in a sample can travel at different speeds. That's what we're really looking at with velocities. However, the distributions of speeds follows a pattern called a Boltzmann distribution. And again, at any given time, one helium might be moving a little bit faster than another helium. So instead, what we look at is a distribution, where we're looking at the fraction of molecules and the molecular speed. And where that top is, that's where we're considering that most of our molecules, that's the speed they're going. Where some might be slower and some might be faster, but most of them are going at the top of that distribution. So when we talk about average velocity of the molecules, there's a couple of different ways we could take this kind of average. The main method of choice is typically root mean squared, and this is just an equation that you have to know. Where our RMS, average velocity, or URMS is the term that's used, is the square root of the average of the sums of the squares of all the molecular velocities. So what we have is that remember, this is sum, we've seen this before, of v squared over n. So u squared is the average of the squares of the particles. We're going to get more into this. Don't worry. I'm not just going to show you an equation and that's it. We can relate this to kinetic energy by looking at the fact that, I got 5 minutes. Ke average is equal to 1/2 of Na, where Na is Avogadro's number, times n and u squared. Or we can look at it as K, our kinetic energy average, is equal to 3/2 RT. Now, R is a different gas constant. Technically, it's the same gas constant. It's just in energy units instead of a different unit. You cannot use this R in PV equals nRT. This is this R. And this is 8.314 joules over mole Kelvin. So this is just different units. These units are related to energy. Joules is a common energy measurement. And joules is equal to kilograms times meters squared over seconds squared. What's velocity? Meters over second. That's where you're getting that energy unit. So this is a gas constant. This can only be used for the equations that we're talking about right now. Do not use this gas constant PV equals nRT. Don't use the gas constant for PV equals nRT in this, because they're different. They have different units, and if you're following your units, it'll be apparent because joules isn't in our 0.08206. So that's, if you follow your units, you won't have a problem. So don't confuse this with our ideal gas constant. That's only used for PV equals nRT. Or it's just a general term for a constant. So you need to know which constant you're using. So what we can do is take that equation we were looking at earlier, and we can equate Avogadro's number times our mass gives us our molar mass. But because joules is kilograms times meters squared and seconds squared, we're going to equate this to molar mass in kilograms per mole. Remember, the molar mass from the periodic table is grams per mole. But grams won't cancel out with this. So it's going to be in kilograms, which we can do that conversion. So if we want to know our root mean squared velocity, we can use 3RT over Avogadro's number times n, or just to be easy, we can use 3RT over our molar mass. What this says, bigger the molar mass, the slower the velocity. That's what that relates. So all you got to do, if you're calculating your RMS, and also notice, if your molar mass is bigger, your velocity decreases. If your temperature is bigger, URMS is a bigger number, so your velocity increases. So that all makes sense. So I'm going to stop there. We'll do some examples where we calculate URMS on Monday and finish up this chapter. We're pretty much almost done. Y'all have a good weekend. If y'all do anything this weekend, be careful, be safe.
It's going to be cold.
It's going to be cold. Stay warm.
We're getting